proximity of the coursework deadline. So if you didn't get yourself a handout last time, or you forgot to bring it along this time, there was a huge stack of the spares at the front, which I can see is circulating now. So do make sure you get one this time. We'll be picking up halfway through that double deck because this is the second hour of that deck. So I'll just do a little recap. I won't recap it all because it would take an hour, but I will recap some of it so that those that weren't here kind of can pick up. So we started talking about the mathematics behind camera projection and how we could model this process of creating an image from a 3D object. And right now we're talking about this in the context of computer graphics, imagining that we're modeling a 3D object and we want to make a 2D image of it to draw on our screen. But as we'll see in a moment, we'll start talking about it the other way round, about how we can reason about the shape of 3D objects from 2D images. In other words, the computer vision problem rather than the computer graphics problem. So let's just recap the basics. So we talked about this last time. This device up here is called a camera obscura, or sometimes just called a pinhole camera. It's basically a box with a pinhole on the front of it that lets light in. In this slightly more fancy version, the guy is, basically there's stuff in the outside world, light from the outside world is coming in through the pinhole, and instead of falling on the back of the box, it's hitting this mirror and shining up onto the top of the box. But the principle is the same. Basically, an image is being created of the world through this process of what's called pinhole camera projection. So what's actually happening is there's a 3D object out in the world. Light is bouncing off that object. It's traveling in a straight line from the object to the pinhole, and passing through the pinhole and landing up on an image plane at the back of the box. And that is causing an image of the object to appear upside down on that image plane, right? So in this simple diagram here, we're just looking at, this is the pinhole, this is the box of the pinhole camera, and this is the back of the box where the image is being formed. This is the tree out in the world. Then what we're seeing is this tree exists at some distance z from the focus, and the tree is at some height y, so we're just ignoring the x coordinate in this diagram. This is just z and y, okay? And what we're what we're seeing here is that the image plane is at a distance d from that focal point. So this is d is the depth of the box. Call that the focal length. Now, when we model this mathematically, we just simplify things by putting the image plane in front of the focal point. So in this setup, we have the 3D object, we have the focus, where all the light rays will intersect, and then we have this imaging plane. And the analogy was, I talked about last time, is having a tree out in the world. We're looking at it through a window from this room, and I'm at the focus looking through the window, which is our imaging plane, out into the 3D world. I'm looking at the height of the tree on the window. Anyway, in either case, the height of the tree, the height of the image of the tree is y prime, the height of the real tree is y, the tree is a distance z from the focus, and the image plane is a distance d from the focus, or focal point of the camera. And we saw that we could reason about these quantities just by recognizing this as a system of similar triangles. It's two right-angled triangles, and the ratio y prime over d is equal to the ratio y over z. And what that means is we can calculate the height of the tree trivially by just saying, well, multiply both sides by d. Y prime is equal d times y over z. Okay, and that's how we calculate the height of the tree. And we could do the same thing for x. We could say the width of the tree is x prime equals d times x over z. So it's just this linear relationship that's getting modeled. And we saw that we could use this matrix multiplication to create that effect, and I won't dwell on that. Calling that matrix multiplication P that performs that projection, that applies that maths, we saw that then we could think about this process of creating an image from a 3D object as just a compound matrix transformation. If we have a point P in 3 dimensions, which might be our tree that we've modeled inside our computer, for example, in computer graphics, like in a CAD package, then we could position the camera relative to that point using some rotation of the camera to orient it and some translation of the camera in the 3D space. And we could represent those transformations by two matrices, T and R. And we talked last time about how these translation and rotation matrices generalize to 3D from the 2D examples we'd seen previously on the course. And then having positioned the camera, then we perform this projection, this perspective projection using matrix P to get the image of our point P prime, which lies on the imaging plane at the distance D from the optical center. And we saw that because these matrices are expressed in this homogeneous form, we can just simply multiply them together to create pi, which is a compound matrix transformation that does all of that. And we call that the camera projection matrix. And we can observe that the components of this camera projection matrix then are some transformations that move the camera about, that position the camera, specifically the orientation and the position of that camera. And we call those parameters of this system the extrinsic parameters, sometimes just called the external parameters, but more commonly the extrinsics. And they're talking about basically the relative position of the camera to the object in the world. And then we're talking about the intrinsics as being the internal parameters of the camera. And so far, we've just talked about the internal parameter of the camera being the focal length. But what we'll see later on today is that there are a couple of others as well. So P encodes the intrinsics, R and T encode the extrinsics. Together, they make the compound matrix transformation pi. And we can think of it as having this form, as I say, a P, an R, and a T. The T is of this form, it's a translation, identity, 3 by 3 matrix, and in this case we're expressing the position of the camera as a negative C. We'll talk about that in a moment, but that's basically 3 numbers there. We've got a rotation, which is a 3 by 3 matrix, which again we could consider to be 3 degrees of freedom, the Euler angles. We talked about those last time. And then we have, and they encode the extrinsics, and then here we have this projection matrix here, and the projection matrix here has just been expressed in a form where it's K times this matrix, which, again, I explained this last time, the projection matrix is often expressed like D1 instead of 1, 1, 1, but here we're expressing it with the ones there, and the extrinsic matrix is a 3 by 3 matrix that applies a scaling factor on that projection, a scale factor of D. So basically K is D1 down its diagonal, and that's applying that scaling onto the projection matrix to make a projection matrix which has D instead of those ones there on the first 2 rows, and that then is the P we were talking about before. And if I flip back, you can see it's equivalent. It will then be equivalent to this shorthand version for P that we talked about last time, which is on the top right there. So that's the summary of where we got to last time. The summary is, if I've got a 3D point P and I pre-multiply by this pi matrix with a camera projection matrix, then it's going to produce me an image P prime in 2 dimensions of that point on the imaging plane Z equals D, where D is the focal length. Okay, so let's move forward and just think about that system in a bit more detail now. So now I'm going to attempt to draw a 3D diagram instead of a 2D diagram. So we're going to have the X coordinate in it as well now, so the Y and the Z. So let's imagine that we have a camera, and that camera is, just as before, imaging this 3-dimensional object, this tree, and we're going to talk about a point in the scene. Again, it's going to be just the top of the tree. And that ray of light is passing through the imaging plane and crossing the camera focal point, what we call the focus of the camera. And all light rays will cross that point. So this setup is no different than last time. It's just we're introducing it in 3D now, and we're going to have a bit of notation here. Let's imagine this point we're imaging has coordinates x, y, z. It's creating an image at uv, and this system all exists now within this three-dimensional coordinate system. Okay. And in practice, this imaging plane might be, a CCD sensor or sensor in the camera. Okay, so this focus then of the camera, so we have a special name for it. We call it the center of projection, and I'll just refer to that as COP from now on, which is basically, as I say, this point in the 3D world that all the light rays are converging in the camera. and this distance then of the image plane from the from the COP central projection is this d that we've been talking about before, this focal length. The other sort of new part then of this diagram we're going to introduce here is this terminology, the optical center. And this is where what's called the optical axis of the camera punctures the image plane. So if you think about the optical axis as being the axis that's perpendicular to the image plane, passes through the focus, the COP, then that was equivalent to the z-axis in the previous diagram, right, in the 2D diagram. And this is intersecting the image plane, pretty much in the middle there, and that is what we call the optical center, and that has the coordinates cx, cy on that imaging plane. Okay, does that make sense? Right. So basically nothing's changed except I've drawn it in 3D and named a few variables and introduced this terminology, optical center. So let's just remind ourselves then what the previous diagram was. We had the COP, we had the focal length, the d, but now we're just calling, instead of y prime, we're calling it u, and we're saying u is d, d times y over z, and v equals d times x over z. And in that previous diagram, we made the simplifying assumption that the central projection of the camera was at the origin of the three-dimensional space that we're talking about. Okay, in other words, that the camera's focal point, or COP, was at the origin of the world, at position 0, 0, 0 in the world, and that the camera was oriented such that the z-axis of the world was aligned to its optical axis. And you see how we made that assumption in the diagram there? Because we were talking about a camera here that has an imaging plane, but that imaging plane could equally, it's a plane in space, it could go negative as well. So we could have rays going under here as well. So the optical axis of the camera is aligned to the z-axis there of the space. Does that make sense? Okay. So that simple diagram and the simple maths, those just ratios there that we came up with last time, are only valid if the camera's center projection is at the world origin and the camera is oriented in this way, which is, of course, a very special case to have your camera in that position. So we need to start thinking about what happens if the camera is not oriented in that way and not positioned exactly at the origin. And this is why we need to start thinking about things like the optical center. And the optical center also lets us account for the fact that when we are reasoning about the position of points in an image, it is normal for us to reason about an origin in the image that is in the top left of the image. That's where point 0, 0 normally is in terms of pixel coordinates on an image. But again, when we're talking about this simple diagram that I drew last time in 2 dimensions, then the origin actually is in the middle of the image, right, at the optical center. Yeah. So we need to correct for that and make the origin of our coordinate system that we express uv in relative to the top left of the image. Does that make sense? So before I go any further, has anyone got any questions about this construction? Does everyone see what's going on with the geometry here, or want to ask any clarifying questions? Yeah.
Is the z-axis the same axis as what is going through the origin of those 3 red lines and the optical center?
Yeah, so what I've tried to draw here, and I admit it's a little bit unclear, right, the coordinate system of the world is meant to be indicated by those red lines there, the x, y, z, and what we're saying is that the camera, its focus, is right at the origin of that space, so is at coordinate 0, 0, 0, and we're saying that the camera is oriented such that its optical axis is aligned to the z-axis of the space. Yeah? Any other questions? Okay. Right, so let's first of all deal with this coordinate system issue in 2 dimensions, because it's the easiest thing to deal with. As I say, in our original construction, the origin was at the optical center, but we want to express the coordinates of the image of our tree, of our point P, in terms of a natural coordinate system for that image, which has the origin at the top left. So if we call the coordinates of the optical center, the point at which the optical center, at which the camera's optical axis punctures the image plane, if we call those coordinates cx, cy, then it's going to be trivial to correct from our simple version of the maths to this more general case, because all we need to do is just express them as an offset from a different origin. And we know how to do that. We just say, well, if we take away cx from u and take away cy from v, then we are going to... oh, a bit of a typo here because I've got dy there twice. I guess you can see what I'm saying. I'm taking away the x and the y components from C in order to come up for a corrected coordinate system. So now we're expressing as an offset from the origin being in the top left, which is the blue set of equations, rather than from the optical center, which is the purple set of equations we had before. So in other words, our u is going to be equal to dx over z plus cx, and our v is going to be equal to dy over z plus cy. So this then lets us account for the size of the image plane and the coordinate system that's defined within it. Okay, so that's dealing with how we like to express our u and v, but let's deal with the more significant problem of the fact the camera could be anywhere in the space. It could be translated anywhere in the space, and so, for example, if the origin of the world was over here, then the camera could be expressed as an offset from that, and obviously the camera could be rotated in any position in the space as well. So actually, we come up with this set of mathematics here to fully express the image of our point P, uv, and that is to take our point P, apply a rotation and a translation to it, to come up with these values, let's call them x, y, and z, and then stick those values x, y, and z into the math that we already have, which takes into account the optical center now, in order to calculate the coordinates uv as an offset from the top left of the image plane. In other words, the pixel coordinates of the image of point P. Does that make sense? Yeah? So that purple box is super important that you remember and understand that. That is the set of equations that lets us move from a three-dimensional point, P, to a two-dimensional point, UV, where UV are the pixel coordinates in the image that the camera is capturing. Okay? Where are the extrinsics in that box? Where are they encoded? Remember, the extrinsics are the external parameters of the camera, basically its position and orientation, T and R. And where are the internal parameters encoded? D, and we've also now met two other internal parameters of the camera, which are Cx and Cy, the optical center. So the intrinsics are the optical center and the focal length, yeah? Also note that we could, if we wanted to, have a different focal length for the x and for the y equation, yeah? And we'll see later on that we tend to model in this way. Now, it doesn't really make sense in a kind of geometric sense to actually have two different values for the optical center. After all, the image plane is just a fixed distance d away from the cop, but the mathematics allow it, and in fact it's useful to express the mathematics with that degree of independence due to errors in camera calibration processes that we'll talk about later on the course. So I guess this slide is just summarising what I just said about the extrinsics and the intrinsics. So so I just mentioned this bit of terminology about calibration. So this is a term we use in computer vision. We say that if we know where the camera is and what its internal parameters are, we say that we have a calibrated camera. And once we have a calibrated camera, we can start doing things like reason about the image of P in an image, the coordinates of the image of P in an image that's been captured by that camera. Okay, right. Before I go any further, has anyone got any questions about this? I'm happy to take them.
Just which way round T and R work, whether it's the position of the camera relative to the world, or whether it's the position of the world relative to the camera.
Yeah, that's a great question, and actually we'll come back to that. So yeah, and it's actually based on just a convention, because you're quite right. If you're talking about shifting the position of the object relative to a fixed camera, then that would be applying some R and T. But if you're talking about shifting the position of a camera relative to a fixed object, it would be the inverse of those transformations. And we need to think about that. And as long as we're consistent one way or the other, it doesn't matter. And you'll see later on that the math is expressed the other way around. Okay, so one question might be, well, what can we do with this math? Okay, well, we're already at the point where we can start talking about a really useful application of this geometry, and that is to build a 3D reconstruction of an object. And excitingly, we have a real implementation of this here at the university in our centre, CVSSP. We have a big TV studio that we can build 3D reconstructions of actors performing in. And the system, I'll describe it to you, basically involves a bunch of video cameras that are in a big circle around the perimeter of the studio, and they all point inwards into the studio and capture the same area of the studio. And basically the volume of three-dimensional space that they intersect, that all the cameras can see, is what we call the capture volume. Okay. Now, I'm going to describe to you now a process of building a 3D reconstruction of something in that capture volume, which could well be a person, could be anything. The method involves decimating the three-dimensional volume of the studio, the capture volume, into tiny little cubes. And we call those cubes voxels. It's basically like the 3D version of a pixel. Okay, so what we're going to do is take the world space, the x, y, z, and we're just going to quantize the x, the y, and the z axis into small units. And typically that would be something like, centimeters squared, maybe, something like that. Okay, and the process of reconstructing the three-dimensional shape of the object in that studio is going to be the process of deciding which voxels are occupied or on, filled by the performer, and which voxels are empty or off. Okay, so we want to make a binary decision on every voxel, and once we've done that for every one of those tiny little voxels in our 3D volume, then we're gonna have built our 3D reconstruction of the object. Okay, which might look like this. Okay, so how are we going to do this? In the sort of simplest incarnation of this studio, what we'll do is we're gonna have blue curtains everywhere. To create a background of a constant colour. What we're going to do is actually within each of our views that we're capturing from our cameras, we're going to create a binary mask, a black and white image where white pixels are the performer and black pixels are the background, in other words blue. So we've already met this task before. How would you go about creating such a binary mask from that image? Yeah, brilliant. So you would build some form of color model of the background. For example, you might take a patch of background pixels and build an eigenmodel of the RGB values. And then you could visit every pixel there and calculate its distance in RGB space from that eigenmodel using the Mahalanobis distance and just threshold it at some sensible value. Okay? Yeah, absolutely. So we already know how to do this. You've got a performer, and we're going to turn that image of that performer into a binary mask. Okay. Now, if you think about it, that binary mask, which of course is really being formed on the image plane of the camera, on an image the camera has taken, you can almost think about that as creating a prism into the world, where if you looked at the perimeter of that binary mask, and you thought about all the light rays that had to be shot from the center of projection of the camera, the focus of the camera, to intersect each of those points on the perimeter, that would carve out like a prism out into the three-dimensional world that started at the focus and then just sort of went out into the world. In fact, if you did that for every single white pixel now, not just the perimeter, you could think about those rays intersecting all the voxels that could be occupied by that single object, right? Now, it's going to intersect a whole lot more than that, because if you were to trace a ray of light from the center of projection of that camera through every white pixel there in our binary mask, it's going to intersect not just the voxels occupied by the performer, but a whole bunch of voxels in front of and behind the performer as well. Yeah? Okay. So what we're going to do is exploit then the fact that we have multiple points of view, and we're going to think about all of those prisms that those cameras produce, and think about where they intersect in the 3D world. Yeah? And that intersection is going to be the 3D volume of the performer. And we call that the visual hull of the performer. Yeah? Does that make sense? Okay. So how could we calculate that? It sounds like a complicated thing to do. Well, it's not. It can be done just with this simple bit of pseudocode here. What we're going to do is iterate through every voxel in the space, which has got some coordinate x, y, z. Let's talk about just a single iteration of this loop. So we're talking about a particular voxel x, y, z. We're going to initialize a counter to be 0. And then for each of our viewpoints, and by the way, each of these viewpoints is a calibrated camera. Through some process we're not discussed yet, but we will cover later on, we have calibrated that camera, so we know its extrinsics and its intrinsics. Okay? We are going to project that voxel's position, x, y, z, to the image plane of that camera. We're going to calculate the UV from that x, y, z. How are we going to do that? Using the purple box that we covered a few slides ago. Okay? And if UV is a white pixel, is set, then we are going to increment that counter. Now, a voxel that is part of this performer in the 3D world, when I project it to each of those camera's planes, it should land up in a white pixel in every one of those camera planes. So if my counter, by the time I've done this for every view, if my counter equals the number of views, the number of cameras, then we're going to consider that voxel to be part of the object, otherwise it's not. And that's how we make our binary decision as to whether that voxel is part of is on or off. And that's ultimately how we come up with our model of the performer. Yeah? So as I say, how do we perform that projection? Just using these equations. We know D, Cx and Cy because we calibrated the camera. And we know R and T as well because we calibrated it too. And then we take our point P, plug it through these equations, get the UV, and look up at pixel location UV whether it's a black or a white pixel in our binary mask. That make sense? So just using these simple equations, which have just been derived from the pinhole camera model, then we can come up with an algorithm for performing 3D reconstruction from multiple views. Now, the assumptions made in this system are that we can image the object simultaneously from multiple points of view. So the cameras, the shutters on all of those cameras fire at the same time. Yeah. Because actually what happens in the studios with their video cameras, and we're doing this 25 times a second, so we're capturing a 3D video of the performer, yeah, a sequence of these voxel volumes. But anyway, the fact we're doing it with video is kind of irrelevant. It's just the same process for every frame. So it's important that the views are taken simultaneously, or equivalently, if you wanted to just do this for a static for a single photo, you would need to have a static object. You could have a stationary object and then just walk around it and take photos of that object from multiple points of view and know the calibration for each of those points of view in order to do the same thing. The other assumption that's being made here, and we talk about it later, is the fact that we're assuming we're using a pinhole camera model. Okay, so it turns out that actually cameras don't really look like this. Yeah, they look like, let me go back to the 2D version. All the way back. Yeah, cameras don't really look like this these days. Okay, with a pinhole, they have a lens in them. Okay, and that lens means that, in fact, this ratio, it's not a ratio anymore, it's slightly non-linear. But if you buy a camera with an expensive enough lens, then you can well approximate it with these equations, and this is what we do. So I don't know if this is going to play actually. I don't think it will, disappointingly. But anyway, this is a single frame of reconstruction of someone dancing in the studio. And if you do this 25 times a second, then you get a moving 3D object. Okay, so before we go any further, oh yeah, there is a question. Yeah.
Do the equations assume that the object is at the same point within the frame, so it's in the same position? It doesn't matter if the same object is in a different position in the frame for the reconstruction?
I don't really understand your question. Sorry, just say your question again.
The object that we're analyzing for 3D reconstruction.
Yeah.
Does its position in the frame affect how you apply the equations in order for 3D?
No. No. So the question is, does the position of the object in the 3D world affect how these equations are applied? No, they don't, because they don't, because the position of the point, the voxel, is an input to these equations. The constants are the camera calibration parameters, which is basically RT, D, CX, and CY, and then the output is UV. So no, those equations will be constant for every single voxel that you process. Any other questions? Okay. All right, so let's then move on and talk about the second application of this geometry, and this is not so much about going from 2D, from 3D to 2D, which is the process we used in that purple box in order to project voxels to 2D to create this 3D reconstruction. We're going to talk about some maths now that lets us go from 2D to 3D, and specifically what we're going to do is look at two different points of view of an object, if you like, two photos of an object taken from different points of view, and we're going to think about how we can reason about the information in those photos in order to figure out the 3D coordinates of the object being imaged. So again, if we think about our tree and just think about just a single point on our tree, our point P, if we image that point P from two different points of view, and we know the camera parameters, the intrinsics and extrinsics for those 2 points of view, then just from the pixel coordinates of the image of P in each view, we can recover the full 3D location of that point P. We can estimate that. Okay, so that's effectively triangulating the 3D position of P from two images of it, but with knowledge of the camera positions, the extrinsics, and the internal parameters, the intrinsics. Yeah? So we're going to talk now about how to do that. Let's talk about the image of that point P in the first viewpoint, which is the one on the left, as being coordinates u1, v1. And let's talk about its view from a second point of view, the image of it in a second point of view as being u2, v2. And we're going to try and recover P. So P here, in other words, X, Y, Z, they are unknown this time, whereas with the visual whole, that was our input. We're going the other way. Okay. Well, the first thing to say is, and let's just start reasoning about just one of the viewpoints now. The first thing to say is that obviously if we're trying to go from 2D to 3D, we don't have enough information to do that. That's why we need multiple points of view to recover the 3D coordinates. So if I'm talking about taking the coordinates of an image of P and reasoning about the unknown, the location of P, then from a single image, I'm going to come up with a multitude of possible solutions. And these, of course, will all lie along the light ray that goes from the true location of P through the image of P and ultimately, of course, through the focus where all light rays intersect. Okay? So it's better to then think about forming an equation for a ray of light that starts at the center of projection of the camera and then shoots out into the world through the image plane and ultimately through the point P we're trying to find. And what we're going to do is reason about this ray from 2 points of view and calculate the intersection of those two rays. Okay. So, well, we already know how to how it's convenient to model an equation for a line. We talked about it a lot when we talked about curves. This parametric form of a line where we have some p of s equals a starting position plus s times some vector. So then previously we've been talking about the starting position being x0 and x1 being the direction. So in this case, we know the starting position. The starting position is the central projection of the camera. And what we're going to do, well, here on this slide at least, is assume that is just at the origin. And then we also know the 2D coordinates of this point P, and we can express that in terms of an offset from the optical center by just subtracting the optical center from it. So now, if we talk about, instead of UV, we talk about U minus CX and V minus CY, then we're talking about that 2D image of that point P now expressed as an offset from the optical center. Okay. So, if the 2D coordinates of this point, this image of P, expressed as an offset from the optical center is U minus CX, V minus CY, then the 3D coordinates of that point with respect to the central projection and the origin of this system is just going to be U minus CX, V minus CY, D, because we know that all points have been projected onto the image plane at D by that perspective projection equation, that we talked about last time. So the 3D coordinates of that image of P, which we call P prime here, are U minus CX, V minus CY, D, making this simplifying assumption that this is where the central projection is. So the light ray starts at the center of projection and travels in the direction D, where D is vector quantity, which is equivalent to our x1, is this set of is these just normalized for convenience. So the parametric equation then of this ray is just x0 plus sx1, or here central projection plus sd, or because the central projection here for convenience is at the origin, it's just sd. Yeah. Right. That was our simple construction. Now, of course, the camera could be somewhere else in the world, not at the origin. So we're going to use this more general form where we do have to think about the central projection. And that central projection, that focal point, could be any translation from the origin, and the camera indeed could be rotated by some r. So in this case, because we're talking about the position of the object relative to the camera rather than the camera relative to the object, picking up on the question earlier, we're going to talk about this the other way around. So we're going to talk about this as being some inverse of the rotation multiplied by the inverse of the translation. And if we talk about the translation as just being a translation by some vector small t, some 3D vector small t, which is just the final column of the big T, which is the matrix version of it, without the homogeneous coordinate, okay, then it's just going to be an inverse of that translation. It's going to be negative t, shift negative t. So in other words, the central projection, the coordinates there, in the general case, is going to be negative r inverse t. So our d then in this general form is not just, we're not just talking about central projection plus SD, we're talking about this D being actually R inverse D and the central projection being negative T. So then we end up with this second purple box of equations. We've seen purple box number 1, which let us move from a point in 3D to a point in 2D. The second box then is taking a point in 2D as input and calculating the equation for the 3D ray. Okay, we first of all come up with an expression for the center of projection of the camera, which is negative R inverse T, as we were just discussing. We're going to call that A. We're going to come up with, we're going to take our input, which is our UV, our 2D point, and we're going to correct for the optical center, by which I mean we're going to come up with coordinates u prime, v prime, which are the image of that point expressed as an offset from the optical center rather than the arbitrary origin of that image in the top left. And then we're going to define this direction for the ray B. And we're going to say our parametric line, our ray, is going to start at A, the central projection of the camera, move in direction B, so it's P of S equals A plus SB. And this is just this box is just telling us, given a U and a V, and the camera parameters, the intrinsics and the extrinsics, output an A and a B, which are the coefficients for this parametric ray. So these two boxes are your sort of big takeaway messages from these couple of hours. These are your equations that let you move from 3D to 2D and from 2D to 3D. But really, of course, we're moving to a 3D ray, not a 3D point, because we can't do that from a single image. Yeah? Does that make sense? Okay. So, assuming that we have this black box, or I should say purple box, process that lets us calculate the parametric equation for a line from a single point in each view, then what we're going to do then is just take our image of our point P, figure out its U and V, just by measurement, just figure out which pixel it is, and then plug that through that set of equations to get our coefficients for our parametric line, which we're going to call here, just for convenience, we're going to call it O1 for the origin 1, for basically by which I mean the start of the line 1, plus S slots of D1, which is that direction for the ray. So parametric line number 1, or ray number 1, from our first viewpoint is going to be AS equals O1 plus SD1. And if we did the same for the second viewpoint, call it B. B of S is O2 plus SD2. Our mission then is to intersect parametric lines A of S and B of S. And what we're going to do, and that will give us our point P. But because we're dealing with an inaccurate system here, we're dealing with integer coordinates from our pixels, and also probably a slightly inaccurate camera calibration process to get those intrinsics and extrinsics that we used in our purple box, then actually it's unlikely that those two rays will intersect perfectly. So what we're going to do instead is look for the point in the space that is closest to those two lines. And that's going to be our approximation to that intersection. I mean, it might be perfect, but it probably isn't, so we have to take that into account. And we'll see how to in the maths in just a moment. So is everyone happy with this construction so far? We've got two calibrated cameras. We've got two images of our point P. We want to find P. And we've derived these two equations for lines, and we're going to intersect them, or at least find the point in space that's closest to each of them, and we're going to call that P. Right. So the way that we're going to do this is by looking for the point in P that's closest to both lines, which actually is on the line of shortest distance between the two rays, which are just infinitely long lines, and that line that connects that's orthogonal. Sorry, that shortest distance between those two rays is going to be a line that's orthogonal to both. Okay, so that point P is going to lie in the middle of that line, that short line that's orthogonal to both of the rays. We're looking for the midpoint of that line, and that's going to be our solution P. So let's derive the equations that's going to tell us how far we have to move along each of our two rays in order to get to the start and end points of that purple line. And because we're going to have to solve this as a simultaneous equation, we're going to come up with a different name for the parameter for line number 2, so let's just call it T. So now we're going to talk about equation A of S, and instead of B of S, we're going to write B of T so we don't confuse ourselves. And what we want to do is come up with the equation for this line, dst, which is basically this optimal point b of t minus this a of s, where t and s are the positions we have to move along the lines to position ourselves such that this is the shortest line between the two. I mentioned that this shortest line will be orthogonal to both rays. So the constraint that we have in solving this system is that the dot product of d1, which remember is just the direction of our ray number 1 in the space, the dot product of that with this line d is going to be 0 because they're orthogonal. And similarly, the dot product of d2 with that line equation for that line, that direction of that line, sorry, is going to also be 0. So what we're looking for then, the values s and t, the two unknowns that satisfy those two equations. Does that make sense? Right. So let's step through this one step at a time. First of all, we notice just from defining it on the previous slide that this direction of this line is just b of t minus a of s. Remember, we're solving for s and t to find this best position. So this is our best line. We want to solve for these two unknowns. So d1 dotted by d of st, just expanded out, is this first line here. And similarly for d2 dotted by d of st is this line here. Okay. So these are our two constraints. So we're going to expand out further now. We know that the equation for b of t is our O2 plus t d2. That's just our parametric equation for the line. O2, and this is our t, remember, and this is our d2. And for a of s, it's just O1 plus sd1, but because obviously it's expanded out in brackets, this is turned negative. So we fully expanded these out now, and then what we're going to do is just distribute this dot product across all of these terms. So this becomes d1 dotted by O2 plus t d2 dotted by d1 minus O1 dotted by d1 minus s d1 dotted by itself gives us this line. And if we were to do the same distribution here on this second line here, we see that we end up with this distribution of terms here. Okay, and then if we were to collect the d1s and the d2s, we can tidy this up. We can observe that we've got d1 dotted by O2 minus O1. They're like the negative terms, so we could sort of add those on. So we create those on the right hand side, and then here we have d1 dotted by d1s minus t lots of d1 dotted by d2 taken onto the other side. So these are just rearrangements of these two lines. But what we've got here is all the unknowns now on the right hand side. And although it looks like there are a lot of terms here, remember that these d1s and o1s and d2s and o2s are all constants that we've obtained from our purple box. Yeah? So we have two equations and just two unknowns. So what we can do is write those out as a linear system, because look, we've got s lots of, d1 dotted by d1 lots of s. Remember, this is a dot product, so that's just a scalar. It's a number. And negative d1 dotted by d2 lots of t. So in my linear system, on the top row there, I'm going to put d1 dotted by d1 and negative d1 dotted by d2. And you can see that then if I multiply that top row by s and t, I end up with d1 dotted by O2 minus O1, which I flip back. You see that's the left-hand side of that first row. For the second row, final line there on that slide, you can see that translates to being d1 dotted by d2 lots of s minus d2 dotted by d2 lots of t equals d2 dotted by O2 minus O1, which is the left-hand side of that final line. So we have there a linear system in the form ax equals b, if we want to call it that. where A is just a 2x2 matrix full of numbers, B is just a two-dimensional vector, and X are the things we want to find, our unknowns. So we know that we can solve an equation in this form by just inverting A, pre-multiplying each side by the inverse of A. So X is A inverse B. Yeah? So that then is how we solve for X, solve for our vector X, which contains S and T. They tell us how far we have to walk along those two rays in order to get to the start and end points of that purple line. So if we want to figure out how to get to the middle of that purple line, well, let's start at one end, the A of S end, let's say, and let's add to that vector the vector describing the length of that line divided by 2, and then we'll land up in the middle, and that's our point P. So from two parametric equations for a line, we found the point P that is closest to both of those lines, which is either going to be the intersection of those lines, were that purple line just a point, or most probably it's a small error, and what we're doing is minimizing that error by taking that midpoint. Does that make sense? Okay. So, in summary, and this is a summary from the 2 hours, remember, this is a double deck of slides. In the first hour, which was the other day, we described basically how matrices that we were familiar with in 2D for performing affine transformations generalized to 3D. We looked at, for example, how rotation generalized to Euler angles and the problem of gimbal lock. We looked at how we can combine 2D and 3D matrices to create compound transformations, and we saw how even pinhole perspective can be modeled as a matrix transformation. That was necessary to talk about that compound matrix transformation pi, which is the camera projection matrix. We needed to reason about that in order to talk about projection of points from 3D to 2D and come up with our first purple box, which we could see was used for 3D reconstruction. And we also used similar math to come up with our second purple box, which was this process of going from 2D to 3D, or 3D ray, and we saw that we could apply those equations to triangulate the 3D position of a point given two images of it. But for all of this, we've had to know the camera parameters, the positions and the internal parameters of those cameras. Okay. Right, well that's the end then of that second half of that deck. So we'll have a 10-minute break now, and then we'll start the next set of handouts, which I'll distribute in the break. Thank you.